Hello students, welcome to EPG Pathshala. I am Dr. Devrat Misra from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Dielectric Properties 7 from paper Electronic, Magnetic and Optical Properties of Materials. So students, let us see what we are going to learn in this module. Detailed study of equivalent circuit of the dielectric. Then we will learn about the fundamental interfacial polarization, and you will learn about the frequency dependence of E star. In this lecture, we will talk about the equivalent circuit of the dielectric. A real dielectric may be represented by a capacitance in series with a resistance, or alternatively a capacitance in parallel with a resistance. We consider that this representation is successful if the frequency response of the equivalent circuit is identical to that of the real dielectric. A series equivalent circuit. A capacitance Cs in series with a resistance has series impedance given by Zs, which is equal to Rs plus 1 over j omega Cs. The impedance of the capacitor with the real dielectric is Z equals to 1 by j omega C0 times epsilon prime minus j epsilon double prime, where C0 is the capacitance without the dielectric. Since the two impedances are equal from the external circuit point of view, we can equate equations 1 and 2 to obtain epsilon prime and epsilon double prime. As a function of frequency, we equate the real and imaginary parts separately. This gives epsilon prime is equal to Cs divided by C0 whole multiplied by 1 plus omega Cs Rs whole square, and E double prime is equal to omega Rs Cs square divided by C0 into 1 plus omega Cs Rs whole square, and tan delta is equal to omega Cs into Rs. According to equation 4, the characteristics show a broad maximum at the radian frequency corresponding to omega Cs Rs is equal to 1. Substituting Cs Rs is equal to tau, the condition for maximum epsilon double prime translates into omega t is equal to 1. Tau is the relaxation time, which substitutes for the time constant in electrical engineering applications. Parallel equivalent circuit. A capacitance Cp in parallel with a resistance Rp may also be used as an equivalent circuit as shown in figure 1. Here we have two circuit, one in series, another is in parallel. In series, both Cs and Rs are interconnected, whereas in case of parallel, both the terminals, they are parallel to the two terminals or the two ends of the circuit. So a capacitance Cp in parallel with a resistance Rp may also be used as an equivalent circuit, and the admittance of the parallel circuit is given by Y is equal to J into omega into Cp plus 1 by Rp. The admittance of the capacitor with the dielectric is given by Y is equal to J omega C0 into epsilon prime minus J in epsilon double prime. Equating the admittances and separating the real and imaginary parts gives epsilon prime is equal to Cp by C0, epsilon double prime is equal to 1 by omega into R into C0, and tan delta is equal to 1 by omega into R into Cp. Series parallel circuit. Figure 1 also shows a series parallel circuit in which a series branch having a capacitance Cs and a resistance Rs is in parallel with a capacitance Cp. We follow the same procedure to determine the real and imaginary parts of the complex dielectric constant epsilon star. The admittance of the equivalent circuit is Yeq equivalent is equal to j omega Cp plus j omega Cs divided by 1 plus j omega Cs into Rs. Substituting again Cs Rs is equal to tau, the above equation becomes Y equivalent is equal to omega square Cs Rs divided by 1 plus omega square tau square plus j omega Cp plus j omega Cs divided by 1 plus omega square tau square. Equating equations 10 and 7, we obtain y is equal to j omega epsilon star C0 is equal to j multiplied by omega multiplied by C0 into epsilon prime minus j epsilon double prime. Separating the real and imaginary parts yields, we obtain the equations epsilon prime is equal to Cp by C0 plus Cs by C0 into 1 by omega 1 plus omega square into tau square, and epsilon double prime is equal to Cs by C0 into omega tau divided by 1 plus omega square tau square. From the above two equations, the dissipation factor gives 10 delta is equal to epsilon double prime divided by epsilon prime, which is equal to omega tau divided by 1 plus Cp by Cs into 1 plus omega square into tau square. These equations may be simplified by substituting conditions that apply at the limiting values of omega. A. At omega is equal to 0, epsilon double prime is equal to 0, and epsilon prime has a maximum. The value is given by epsilon prime is equal to Cp by C0 plus Cs by C0 is equal to epsilon s. B. As omega tends to infinity, epsilon prime approaches a minimum value given by epsilon prime is equal to Cp by C0 is equal to epsilon infinity. C. The radian frequency at epsilon double prime, which is a maximum, is given by delta epsilon double prime by delta omega is equal to C0 plus 1 plus omega square tau square into Cs minus 2 omega square C0 Cs into tau square, which is equal to 0, which gives omega tau is equal to 1. This result shows that the equivalent circuit yields omega max that is identical to the Debye criterion. Interfacial polarization. Interfacial polarization, also known as space charge polarization, arises as a result of accumulation of charges locally as they drift through the material. In this respect, this kind of polarization is different from the three previously discussed mechanisms, namely the electronic, orientational, and atomic polarization, all of which are due to displacement of bound charges. The atoms or molecules are subject to a locally distorted electric field, that is, the sum of the applied field and various distortion mechanisms apply. In the case of interfacial polarization, large-scale distortions of the field take place. For example, charges pile up in the volume or on the surface of the dielectric predominantly due to the change in conductivity that occurs at boundaries, imperfections such as cracks and defects, and boundary regions between the crystalline and amorphous regions within the same polymer. Region of occluded moisture also cause an increase in conductivity locally, leading to accumulation of charges. We consider the classic example of Maxwell-Wagner to derive the epsilon prime minus omega and epsilon double prime minus omega characteristics due to the interfacial polarization that exists between two layers of dielectric materials that have different conductivity. Let d1 and d2 be the thickness of two materials that are in series. Their dielectric constant and resistivity are respectively epsilon and rho, with subscripts 1 and 2 denoting each material, as shown in figure 2. Figure 2 shows dielectrics with different conductivities in series. So we have one medium with epsilon 1 and rho 1 and another with epsilon 2 and rho 2. When a direct voltage V is applied across the combination, the voltage across each dielectric will be distributed at t is equal to 0 according to V10 is equal to V into C2 by C1 plus C2 and V20 is equal to V into C1 by C1 plus C2. When a steady state is reached at t is equal to infinity, the voltage across each dielectric will be V1 infinity is equal to V into R1 divided by R1 plus R2 and V2 infinity is equal to V into R2 divided by R1 plus R2. The charge stored in each dielectric will change during the transition period. At t is equal to 0, the charge in each layer will be equal to Q10 equals to Q20 is equal to C1 V10 is equal to C2 V20, which is equal to C1 into C2 divided by C1 plus C2. At t is equal to infinity, the charge in each layer will be Q1 infinity is equal to C1 V1 infinity, which is equal to C1 R1 divided by R1 plus R2 into V, whereas Q2 infinity is equal to C2 V2 infinity equals to C2 R2 divided by R1 plus R2 into V. During the transition period, the change in the stored charge in each layer is delta Q1 is equal to Q1 infinity minus Q10, which is equal to Vc1 into C1 R1 minus C2 R2 divided by R1 plus R2 into C1 plus C2. Similarly, delta Q2 is equal to Q2 infinity minus Q20, which is equal to V into C2 into C2 R2 minus C1 R1 divided by R1 plus R2 into C1 plus C2. The redistribution of charges within the layers occurs due to the migration of charges and equations 15 and 16, so that there will be no migration of charges if the condition C1 R1 is equal to C2 R2 is satisfied, since C1 R1 is equal to epsilon 0 into epsilon 1 rho 1 and C2 R2 is equal to epsilon 0 epsilon 2 rho 2. The condition for migration of charges translates into epsilon 1 rho 1 which is not equal to epsilon 2 into rho 2. Let us suppose that the condition set by expression 17 is satisfied by the components of the two-layer dielectric. The admittance of the equivalent circuit is given by in figure 3, where we have two dielectrics in series for interfacial polarization, from which we can calculate Y equivalent is equal to Y1 Y2 divided by Y1 plus Y2, where Y1 is equal to 1 by R2 plus j omega C1 and Y2 is equal to 1 by R2 plus j omega C2, leads to Y equivalent is equal to 1 plus j omega tau 1 into 1 plus j omega tau 2 divided by R1 plus R2 plus j omega R1 R2 into C1 plus C2, where we have made the substitution C1 R1 is equal to tau 1 and C2 R2 is equal to tau 2. We further substitute tau is equal to C1 plus C2 into R1 R2 divided by R1 plus R2, which is equal to R1 tau 1 plus R2 tau 2 divided by R1 plus R2. Substituting equations 20 and 19 into 18 and rationalizing the resultant expression yields a rather long expression. Y equivalent is equal to 1 by R1 plus R2 into 1 minus omega square tau 1 tau 2 plus omega square tau into tau 1 plus tau 2 minus j omega tau into 1 minus omega square tau 1 tau 2 plus j omega tau 1 plus tau 2 divided by 1 plus omega square tau square. The admittance of the capacitor with the real dielectric is Y is equal to j omega C0 epsilon star, which is equal to j omega C0 into epsilon prime minus j epsilon double prime, where epsilon star is the complex dielectric constant of the series combination of dielectrics. equating the real and imaginary parts of A and B, we get epsilon prime is equal to 1 by C0 into R1 plus R2 into tau 1 plus tau minus tau into 1 minus omega square tau 1 tau 2 divided by 1 plus omega square tau square, and epsilon double prime is equal to 1 by omega C0 into R1 plus R2 into 1 plus omega square tau 1 tau 2 plus omega square tau into tau 1 plus tau 2 whole divided by 1 plus omega square tau square. So there are few conditions, such as in A, when omega is equal to 0, equation 21 reduces to epsilon prime is equal to epsilon s, which is equal to tau 1 plus tau 2 minus tau divided by C0 into R1 plus R2. And the condition B is that as omega tends to infinity, epsilon prime is equal to epsilon infinity, which is equal to tau 1 tau 2 by tau into 1 by C0 into R1 plus R2. Substituting equation 23 and 24 in 21, we get epsilon prime is equal to epsilon infinity plus epsilon s minus epsilon infinity divided by 1 plus omega square tau square. A further substitution of equations 23 and 24 into equation 22 gives epsilon double prime is equal to 1 by omega C0 into R1 plus R2 plus omega tau into epsilon s minus epsilon infinity divided by 1 plus omega square tau square. Equation 25 gives the epsilon prime versus omega characteristics for interfacial polarization. It is identical to the Debye equation, that is, the dispersion for interfacial polarization is identical with dipolar dispersion, although the relaxation time for the former could be much longer. It can be as large as a few seconds in some heterogeneous materials. The relaxation spectrum given by equation 26 has two terms. The second term is identical to the Debye relaxation, and at higher frequencies the relaxation for interfacial depolarization is indistinguishable from dipolar relaxation. Frequency dependence of epsilon star. We are now in a position to represent the variation in the complex dielectric constant as a function of frequency from omega is equal to 0 to omega that tends to infinity. Figure 4 shows the contribution of individual polarization mechanisms to the dielectric constant and their relaxation frequencies. As each process relaxes, the dielectric constant becomes smaller because the contribution to polarization from that mechanism ceases. Beyond optical frequencies, the dielectric constant is given by epsilon infinity is equal to n square. Figure 4 shows the frequency dependence of the real and imaginary parts of the dielectric constant. So it's a schematic diagram. The orientational polarization occurs in the radio frequency to microwave frequency range in dipolar liquids. However, in polymers, the dipoles may be constrained to rotate or move to a limited extent depending upon whether the dipole is a part of the main chain or side group. Correspondingly, the relaxation frequency may be smaller or of the order of a few hundred kilohertz. Further, in solids, there is no single vibration frequency but only a range of allowed frequencies, making the present treatment considerably simplified. The experimental results presented in the next chapter in a number of different polymers will make this evident. So students, let us summarize what we have learned in this module. In this chapter, a detailed description of equivalent circuit of the dielectric was given. In addition, the fundamental of interfacial polarization was studied. We also learned about the frequency dependence of epsilon star. Thank you.